that I sent before. So actual beginning of the lecture. So here are the equations that we should get acquainted with. So by the end of the lectures, we should have clear understanding what they are. So let me invite you to share your vision of and maybe comments how you interpret this equation, what you do not like in it at most, or anything you can say about it. So and I understand that it is not a fair game because I didn't present anything. So it's only a pedagogical trick. So if you start discussing it ahead, it will be much easier to get over this material together. So Lola, would you like to start and share any comments?
Are any comments concerning what?
Like, what do you think about these equations, either first or second? How do they relate to the flow chart of DFT that we covered last time?
I have no idea.
Like, it is normal. Do not worry. So, how would you interpret the letter rho in the upper equation? What typically we call this letter rho?
Density, total density.
Yeah, very good. And how would you interpret the letter E?
Energy.
Okay, so this is an equation that converts total density into total energy, right?
Okay.
And the in the second equation, oh, maybe enough. We need to. Thank you, Laura. You answered correctly. Sarah. So,
yeah.
Would you please comment on the second equation? Do you see any symbols that you recognize?
Maybe it's this equation is kind of relating the density to the potential.
Yes, exactly. So it converts density to potential. And equations at the top and the bottom, they are not tightly related. They are for different so-called functionals. But do you see an observation? What's the difference in the power of the density in the upper equation and lower equation?
Yeah.
So what will be the subtraction of this power? Like if one tries to take this 4/3 minus 1/3.
1.
Okay. Any ideas? Is it coincidence or maybe there is something behind it?
Maybe because of this constant Cx, or we have a constant value before the integral for the above equation. Maybe this constants play a role. These powers. I'm not sure.
Okay. And what is the connection between density? Between total energy and potential. How do we obtain the potential out of density? Let me bring in the part that we covered together last time. So what is the connection between density and potential? Oh,
Energy?
energy and potential. Yes. What's the connection?
Density.
But can you verbalize which operation brings us from energy to potential?
Derivative?
Yes.
Derivative of total.
Yes.
Partial,
Exactly.
partial derivative.
Functional derivative. So typical derivative is d. Partial derivative is this flipped 6, and functional derivative is delta. Okay. Yeah. Yeah. Thank you much, Sarah. Kia, would you please share any observations on this? Anything else you can identify in this equation, or anything that you like or anything you dislike?
There is one sign. What's the? It's not like a E. It's I forgot the name.
Oh, okay. Psi, Greek psi.
Yeah, yeah. So Greek psi is the in the numerator. It's the subtraction of the two density, maybe.
Mm-hmm.
If there is a two type of density, it's the subtraction. It's and divided by the summation of the density. So
Okay.
what is the meaning of that?
So rho alpha and rho beta are densities for alpha and beta electrons. So
Yeah.
they are needed for spin polarized. And if we have a singlet, if densities for alpha and beta are the same, then this parameter will be 0. So
Okay.
we will have nothing here, and then it will be just a constant. So in absence of spin polarization, the term here will disappear and will be just a constant. Yeah, thank you for observing it. Okay, Lina, would you like to share any comments?
So I just noticed the minus sign here in the potential relation. It wasn't in the energy relation with the density.
Okay. Yeah, thank you. And anything else?
No, everything is clear.
So how would you interpret the parameter x? If you want to describe, if we don't have screen and we need to speak about it by human words.
So as we know, the potential is always related to the position of the particle. It's a position.
But no. Here is a definition of x, and x is not position. It is defined as what does this triangle symbol mean?
Sorry.
What you see, there is a little triangle symbol. I will highlight it with red.
Triangle.
What does it mean?
Which triangle?
Here in the upper lower right.
Okay.
Gradient?
Yes,
yeah.
exactly, gradient.
No, I didn't see it before. It was video.
Okay, so x is a gradient of density.
Yeah, gradient, which means derivative.
Derivative of space. So sometimes if one needs to get more exact, more precise equations for the connection between density and energy, or density and potential, one needs to involve also gradient of density. And here is an example how it is done. Okay, yeah, thank you very much for the discussion. I think the rest of the lecture will go hopefully pleasant and easy. So I'm going to focus your attention on the figure that the last figure we did in the lab for spin polarized density of states, and there is a thing that we didn't have time to do, but for this spin polarized triplet or other similar configurations, one can also plot orbitals. And remember, when we were dealing with Gaussian, there were alpha molecular orbitals. When we were using the CubeGen, you can use AMO and BMO for alpha molecular orbitals and B molecular orbitals. So this same technique is available in VASP, and it will be playing a role if we do spin polarized density of states, for example, triplets. And examples of the orbitals are stored in the memory of VASP in a little bit different way. So if we play Gaussian, it shows alpha and beta molecular orbitals, but VASP instead stores information in a form of summation of alpha plus beta orbitals and or subtraction of alpha minus beta orbitals. And this is more natural way. It's not as visual for humans, but it is more natural for computations because it is what is used in the procedure of converting density into functional. So some of you may have asked yourself, or maybe you developed irritation against instructor inside yourself about why at the end of the last lab we spent time doing triplets. What are the models or triplets and generally non-single configurations anyway? So before going to equations, we will discuss it. And even before that, let me comment on the subject that Sarah did notice, but we may want to discuss this subject once again in a little bit more details. So the energy as function of density is obtained in so-called local density approximation. It's simple. So functional. Just a second. In Thomas Herming theory, the energy is integral of density into the power 5/6. If we do simplest functional for the real life, the change is not as big. One just there are reasons to change power from 5/3 to 4/3. And one can represent product of this 4/3 as rho to the power 1 or 3/3 times rho to the power 1/3. And if one wants to perform integration not over position in space, but over the density, thinking about functional derivative, this product of density into the first power and increment of position can be merged together and represented as increment of density. So rho dr will be d rho. And if we accept such notation, then we can automatically take derivative. We can practice derivative for the total energy in order to obtain the potential. So potential will be a functional derivative of energy in respect to total density, and we just remove the symbol of integral and remove this delta rho. So the potential will be density into power 1/3. And one also needs to discuss sign and constants, but I'll better skip it. So inversely, if one perform integration of the potential, so we can take this functional derivative of energy over increment of density and integrates it, makes functional integral, then integration and differentiation procedures compensate each other and one obtains back the total energy. So for next 20 minutes, I will make an effort, maybe 25, to get this equation. How the local density approximation is converted into local spin density approximation. So the name for this one, LDA, comes from the fact that density comes in the local fashion. So one integrates over all points of space and one uses only density in a certain point. So we do not subtract or multiply, we do not do any operations for densities defined at different points. We just take in one point and then scan through points and integrate it. So therefore it is local. And since it is not absolutely correct, it is approximation, so local density approximation. If one wants to describe non-singlet configurations like triplets, then one needs to do adjustments for this equation. And I'm going to go over them. So if you have magnetic materials, if you want to describe systems which are explored by EPR, electronic paramagnetic resonance model, if you deal with transition metal ions, with organic complex with transition metals, if you deal with radicals, then one often needs unpaired speeds. At the beginning of the course, we discussed the spin operators in the basis of spin up and spin down. So if we keep behind the dependence of orbital on position and focus only on dependence on spin projection, then one works in the discrete basis of two states. And in order to practice quantum mechanics in this basis, one uses the creation and annihilation operators, which flip spin up or down. And one can compose operators, this S, X, S, Y, S, Z, which would correspond to projection of spin and spin-related magnetization on different Cartesian axes. So +1 + 1 means one adds together projection of spin alpha and spin beta. +1 - 1 means one subtracts projections, and 1 - 1 means one takes the probability to find in the spin up minus probability to find spin down. In order to describe spin, the concept of orbitals that we used in Hartree-Fock and now we use in Von-Schramm orbitals in DFT needs to be updated. So instead of one orbital with a single index I, we have two sets of orbitals, alpha and beta. And for the same index I, one have two orbitals. So we need to make adjustments to our conversion of density into energy with an account of these specifics. So what is possible to do mathematically with this pair of components, with this pair of orbitals? So one can mathematically place this components into a vector. Components into a vector. And then this vector can be represented either as row or column. So let me ask Lola if you would like to comment this this equation that I'm focusing with this arrow.
I don't know what kind of comment.
Like if you have two vectors, one two-dimensional vector, one is row, another is column. What can we do with them?
Multiply.
Yes. And how do we multiply row by column?
I don't know how to explain it. I just know it.
But
you sort of like place the one that looks horizontal, place it vertical, so that you multiply each. Yeah.
Vertical by horizontal, right?
Yeah. Yes.
So please check if I made any errors or I follow this row by column rule.
Yeah, that's correct.
So it is both index I in all symbols. In first, thank you, Lord. In first symbol, both are alpha, and in second, both are beta, right?
Yeah.
And now, if we have phi I alpha star times phi I alpha without star, it is the same as contribution to density. So it's probability density for the alpha, or we can call it phi I alpha absolute value squared. So it will be contribution to the density from orbital alpha. Make sense? No one objects? And the second term will be contribution to the density from orbital beta. So by performing this scalar product, one is getting contribution to the total density from both alpha and beta orbitals. So this part will be needed for what follows. The next thing will be not needed for the course in this lecture, but if you do research on magnetic materials in the future, it could be needed. So, Kea, will you please help me commenting on this equation? Your microphone is muted. Oh, okay. So he is you'll be back in 5 minutes. So, Lina, would you like to save the situation and comment on this second equation?
Okay, so comment on the multiplication process.
Yes.
So as we have a column times a row, will be vector like matrix of 2 by 2. So we have the first term of the first column times alpha. So we have alpha first term. So the second will be first times the second, first in the row in the column times the second in the row. So we will get alpha beta, the second term in the matrix, and then beta alpha and beta beta. So that's correct. So we have matrix of 4 elements. So yeah, two-dimensional matrix.
Yes. And how does this object is similar or different from the object in the previous line? Are there any similarities?
Yeah, so the first one is a magnitude because it's giving a scalar quantity, but the second would be directional or vector.
Okay. So the elements contributing from scalar product will be diagonal elements of this orbital matrix, right?
Yeah.
But in addition to this, there will be off-diagonal elements which were not included if we practice just scalar product.
Right.
So yeah, thank you, Lina. Stephen, if you have a mood to discuss, would you try to comment on the similarities and differences of these two expressions?
Could you say that one more time, Professor? I missed a word.
We have two expressions for composed densities composed of alpha and beta orbitals. So one was made as a scalar product and includes only orbitals squared, alpha and beta. And then we have dyadic product, colon by rho. And in addition to this orbital squared, we have off-diagonal elements. So can you just share your impression? Is there any need in the second line, or what is possible projection on any project you plan to do? Just share observations. It's not an exam, and no one of us is expected to have it in the memories.
Well, I feel like I should check this before saying it, but I believe off-diagonal interactions can cause an important change in the properties of materials in certain states, such as superconducting materials and also some magnets.
Yes. So let me make this question even more specific. If we try to find magnetization in the X, Y, and Z direction, would the attempt to find this magnetization in X, Y, and Z direction will be same or different if you take into account those off-diagonal elements?
It would be significantly different.
Yes. And can you guess what will be the same and what will differ? So let me give a hint. For Z projection, we use only diagonal elements. Therefore, for Z projection, whether we use a scalar product or dyadic product, the observables magnetization will be computed the same. But if you look for X and Y, since they use off-diagonal elements in the structure of the operator, then the densities which miss off-diagonal elements will simply do not give any magnetization in X and Y direction. So in the project that we plan to do, we probably will focus only as Z because it is much easier. One can neglect this alpha beta cross elements. But if one does it as a matter of major research, then they need to be taken into account. Whew, thank you, Steven, for support. So if let me ask everyone. Did you ever saw the first equation for spin in magnetic field?
No, I've never seen it.
Yeah.
No. Never.
Never.
So I see yes from Lina, and if you I cannot mandate it, but I would appreciate if you put on cameras, then I can see just your fingers up and down. So Lina told yes, Kia told
Because,
no.
Professor, we learn chemistry in our school level, so it's difficult to solve this kind of equation.
This is not even chemistry.
Okay, Sarah, did you solve this equation before?
No, unfortunately.
Okay, fortunately, then I will feel myself so significant that I'll introduce you to this equation. So, if this is equation of a compass, I'll bring yeah, right here. So, what does compass do? Lola?
Helps you to find your direction.
Yes, and if I move, will arrow of the compass move with me, or it will direct still to the North Pole?
It will direct still to the North Pole.
Why? So there is a let me give you a hint. There is a universal answer which makes the speaker to look smart, even if like if I do not know the answer, I can address it in a way that will look smart. So here is the quote: because it is energetically favorable. Make sense?
Please explain.
So this is a general answer for like 90% of chemistry and physics problems. So you just tell something happens because it is energetically favorable. So the energy minimum of arrow is when it is oriented towards North Pole, which means if it rotates away from the North Pole, the energy increases. So this S is the arrow of the compass. Vector. B is the vector of magnetic field on the globe that goes to the North Pole. So if they are parallel, then energy is minimal. Make sense? And if one tries to rotate the arrow away from this direction, due to the scalar product, the energy will be bigger. And we all follow the principle of least action or least energy. So arrow will resist and try to follow the minimal energy direction. Okay, now in mathematical sense, this equation of compass can be written as a scalar product of S vector times B vector. And S vector contains X, Y, and Z component, B vector X, Y, and Z components. If we want to simplify our life drastically, we can forget about X and Y direction and think only about Z direction, which means our spin or our compass will be one-dimensional. It will be directing only forward or backward, and our magnetic field will be only along the Z direction. You see, it is a very big approximation, but it works in a lot of practical applications, and it also already helps to resolve some things. So under this approximation of field along X and B is zero, the energy of interaction between spin, which is same as a compass, and magnetic field has these two projections. Now, so Boston is not here. I would ask this question to him. So now please give me a little comment who have seen this equation either in previous courses or in this course. So Lena says yes. Steven? Yes. Lola? You can show yes, no, or needs more comments.
Need more comments. I
Okay.
don't remember.
Okay. Yeah. Thank you. Kia, are you comfortable with this equation? Okay. Sarah?
Me need more comments.
Okay. So this is second main equation of quantum theory. First main equation is Schrödinger equation. The second one is how to obtain observable from a wave function. So if one knows a wave function, there is a way to find observable which comes on experiment. An example that we practiced in our labs in class under examples are transition dipole for absorption or energy. So by plugging in operator corresponding to observable between wave functions in such a sandwich, one can get expectation value. And finding expectation value of observable is mathematical representation of most experimental tasks in materials characterization. So when you have an instrument to characterize material, basically you are finding observables. And NMR, UVVs, most things can be formulated in this language. Is it better? Can you all say that this equation is clear? Sarah? Okay. Lola?
Yes, thank you.
Okay, thank you. So, and this was the basic that we all should be comfortable with, and now I'll do a little advancement. If wave function is two-dimensional vector, then we, in discrete form, the wave function with star will be rho, wave function without star will be column, and operator will be a matrix 2 by 2 in this form. And if instead of wave functions we play with densities, then expectation value is formulated as so-called trace operation, which means take the operator of observable and take the density of the quantum state, then multiply them by each other and take diagonal element. So equation of trace means summation of diagonal elements. Now I'm going to practice it for our spins and contribution to spin density. So if I look on the expectation value of the SZ projection, I take SZ operator, I take this combination of densities as a 2 by 2 matrix and perform this row by column operation. So if I do it carefully and get alpha alpha beta beta on diagonal and then alpha beta beta alpha off diagonal. And then when I practice the trace operation, which means I add together diagonal elements, I will obtain this rho alpha alpha minus rho beta beta. So chance that spin is up minus chance that spin is down gives magnetization of material. So if spins are for sure up, it is magnetized. If it is for sure down, it is magnetized. But if it is with equal probability on up and down, then there is in average no spin and system is not responding to magnetic field. So energy of spin in magnetic field. Projection of magnetic field times subtraction of densities.
So Dr. Cohen, so is it just conceptually that alpha beta is 0, right?
So if amount of electrons in alpha orbitals and beta electrons is the same, then the material cannot be magnetic.
Okay.
It will not respond to magnetic field.
So it's just because it's magnetic, we just cancel these two.
I understand your question. I do understand, but the logic goes different way. If you do some system, if you and we compute number of electrons with spin up, number of electrons with spin down, or density of electrons with spin up, density of electrons with spin down, and then we subtract these two things. If this subtraction will be zero, then as a consequence, system will be non-magnetic. If it will be non-zero, then system exhibits magnetic field properties. Why I'm doing this? We are not going to, we are not modeling much of the magnetic properties, but we are not including magnetic field. But through this abstract consideration, we are coming to the simplest concept how to express energy out of density. I just do not know the shorter way. Okay. Now, Sarah, would you like to comment on the top equation?
For the top equation, it's related to density of electrons.
Yes. And just for a second, I'm going to bring part of the flowchart from last lecture. So density is summation of orbitals square of all occupied electrons, right?
Yeah.
And now we add together all orbitals from like first, second, up to HOMO.
Yeah, square. For the upward spins.
Yes, for upward spins. Okay, so it will be density of alpha of all orbitals with alpha spin. Good.
Yes.
What is the second line?
The second one is for the downward spins, beta.
Mm-hmm. So
it's density of the electrons for the downward spins.
Right. And n sub alpha is equal to HOMO alpha, and n sub beta equals to HOMO beta.
Beta.
So if the HOMO of alpha is not equal to HOMO beta, then material is magnetic, right?
Mm-hmm. Yeah.
Okay, and the parameter that we were practicing last time in the lab, n up, down, it is when we set up this n alpha minus n beta. So if we want to specifically constrain how much number of electrons in alpha and beta are different. Okay, yeah, thank you, Sarah.
Yeah.
So now I believe Kia did notice this equation. So if one has the alpha and beta densities, one can add them together and obtain the total density of all electrons, alpha and beta, right? Okay.
Yes, Professor. Yeah.
Okay. Okay. And if one subtracts alpha minus beta, so it will be zero if there are no overall spin, overall magnetization, and it is non-zero if the material is magnetic.
What's and it's called spin density, right?
Yes. Yes. So what would be result of integration of the total density?
It's written here. So when first you need to integrate rho alpha, that means density of the first one, and it's the number of the total number. When you integrate that, you will get the total number of that one electron. Okay, then obviously the plus of the total number of the electron of the beta, And a similar thing will be happen with the -1.
Okay, so adding together number of electrons alpha and number of electrons beta will be total number of electrons in
Yes,
C.
yes.
And subtracting can be either zero or non-zero depending on whether it is magnetic.
Yeah.
So delta n or n up down. Now,
Dr. Kilin,
yes,
sorry, can I take you back a little bit? Which one did you say the between total density and spin density? There was one that you said depicts if they are magnetic or not. Which one is it?
Spin density.
Depicts that they are magnetic.
Yes, yes,
Okay.
exactly. Yeah, thank you, Roland. So, and now another thing that you may have seen in the inorganic chemistry, or if you need to take it, you will see it, or in so this dn is n up down, right? If we divide it by we can divide it by 2 because each spin has orbital angular momentum 1/2 plus 1/2 or minus 1/2. So if we take this difference in number of electrons and divide by 2, we can call it spin. Okay. And now, if the amount of electrons is changed discretely in each orbital, then what are the available values of this delta of number of electrons divided by 2, or values of absolute values of spin? Sarah?
I'm not sure about that.
So if we have n alpha equals n beta, then their subtraction will be
Is zero.
If n beta and n alpha equals n beta plus 1, then their subtraction
is 1.
Subtraction is 1, but if we divide subtraction by 2, will be
half.
And okay, it is here.
Yes.
Right. So if we have n alpha equals n beta. Oh yeah, I think we need to let everyone to speak a little. Yeah, thank you, Sarah. Let me ask Steven, would you like to comment on it if you have wish?
1 second. I accidentally minimized the screen and now I can't get it back. Uh-oh.
But you can comment it even without watching on the screen. Just listening. So if number of electrons with alpha electrons is twice as big, not twice, two electrons are more in alpha orbitals, then the difference will be, or difference in electron in alpha and beta will be.
It'd be a factor of 2, wouldn't it?
Yes, will be 2. And if you divide this difference by 2, 2 divided by 2 will be equal
1.
1. So it will be spin equals 1 because of 2 electrons added together. Right?
Yes.
Okay. Yeah. Yeah. Thank you, Steven. And now, Lina, would you like to comment what will be the total spin if we have 3 electrons more in alpha than in beta?
Yeah, so 3 electrons, 2 would be for 1 and 1 minus 1, minus half, right?
So if you, yeah, so total,
So total would be minus half.
just 3 halves. If,
So plus
if all 3 spins are aligned
3
parallel.
halves. Right. Yeah.
Okay, yeah, thank you very much. Now, the next little thing. There is a so-called quantity as multiplicity, which tells how many degenerate states can be formed by a state with a certain amount of spins. So degeneracy means how many copies, how many orientations of spins. So if we have spin 0, then it is unambiguous. There is no degeneracy. So it's only single configuration. Therefore, and if you plug in 0 into 2s plus 1, will give us 1. Make sense?
Yes.
Okay. Now, Lola, would you like to plug in the value 1/2 into this equation?
Yeah, that'll be 2.
Yes. And how do we interpret it? So, how many orientations a spin 1/2 may have?
1.
No, 2. Once it can be oriented up, another it can be oriented down.
Okay, yeah.
So it's doubly degenerate, and you got this number 2, and therefore this state is called double because two orientations. Thank you. Stephen, would you like to tell what will be the multiplicity if one takes spin s equals 1 and plugs it into the equation 2s plus 1?
That would be a triplet, wouldn't it?
Yes. Can you comment why there are 3 orientations for triplet?
Because it can be up, down, or one either way with 2 electrons.
Exactly. Or both up, both down, and up, down.
Yes.
Excellent. Triplet, there are 3 states, and they have same energy in absence of magnetic field. Lina, would you please plug 3 halves into 2s plus 1?
Yeah, it's now
So 2 times.
Yeah, okay. So we have now 4, and it's quadruplet. So quadruplet, which means we have 4 orientations. So is it up, up, down, down, up, down, and down?
Yeah, it should be all 3 up, all 3 down, 2 up, 1 down.
Okay, yes.
Down, 1 up.
Because there are 3. Yes. Yeah, I got it.
Okay. Yep. Excellent. Thank you. So now definition. Instead of using literal spin density, and I know I already overused time, I will speed up. It is not normalized, but if we divide, because density is as bigger as larger number of electrons, but if we divide subtraction of these densities by summation of these densities, it will be always smaller than 1. And one can reproduce the projections density in alpha or in beta by taking this psi plus 1. So if one plays mass, one will get rho alpha. And if one makes psi minus 1, one will get minus rho beta. And if one multiplies it by rho, so total density times 1 plus psi will be rho alpha. Total density times 1 minus psi will be rho beta. And you can check the math. I was checking myself. It should be correct here. Now, yeah, here it is summary. If one defines this spin polarization density, one can use it to reconstruct back alpha and beta projections. And after that, one can assume that for alpha and for beta, dependence of energy on density will be absolutely the same. We just need to add them together. So if one plugs this rho alpha in 4/3 and uses it in terms of spin polarization parameter, and if one takes rho beta in 4/3 and represents it in the terms of spin polarization parameter, then one can make a functional for spin density. So it will be rho to the power 4/3. We put it out of bracket, and then this combination of the spin polarization. So the simplest functional is LDA, local density approximation. And if we do have spin, then it will be LSDA. And if you look in the drop-down menu in Gaussian, it is the same, the first function you can see. Now, in the practical calculations, we are using PBE function, which would have a little longer formula that wouldn't fit the format of the class, but PBE functional belongs to the so-called class of GGA family of functions, which stands for generalized gradient approximation, which means in order to make conversion of density into energy more precise, one adds additional corrections which depend on the gradient. So if one sets that this gradient equals 0, then this term will disappear and the functional will reproduce back to LDA. So it will be rho to the power 1/3 for potential, and if one integrates it over density, functional integration, it will be rho to the power 4/3. But there is a sub-community of researchers who are doing additional effort in order to find functional form, how these corrections should be added to the LDA functional and make it more precise. So this one is LB functional. Typically, people try to put their first initials and the year when it is derived into the name of the function. So LB94. So I think it is enough. Thank you for your attention, for participation in discussion. Yeah, this one is 22. And everyone is welcome to disconnect